There is a growing pattern in modern astronomy that is hard to dismiss once you notice it. When an observation does not fit existing models, the conversation narrows instead of expands. With the interstellar object known as 3I Atlas, that pattern appears to be playing out in real time. Since its discovery, the public narrative around 3I Atlas has remained largely unchanged, even as the observational data has grown more complex. Official statements from NASA have relied on familiar classifications, presenting the object as behaving largely as expected. Yet early observations were limited, follow-up was inconsistent, and when rare alignments occurred that should have clarified its nature, the resulting anomalies were not meaningfully addressed. The data is available, but its implications have not been emphasized. This points to a more unsettling possibility, not that something extraordinary is being hidden, but that uncertainty itself is being quietly contained. Interstellar objects sit outside the conditions our models were built to explain, and 3I Atlas may be exposing those limits. If so, the real question is no longer just what this object is, but what, if anything, NASA could be choosing not to highlight. From the moment 3I Atlas entered observational range, it became clear that this was not a routine astronomical event. Interstellar objects are not merely rare, they arrive without warning, without control, and without the benefit of decades of contextual study. They cut through the solar system once and are gone, offering only a narrow window to extract meaning from incomplete data. In the case of 3I Atlas, that window revealed a growing mismatch between what telescopes recorded and how the object was framed in official discourse. The data itself was real, public, and measurable. The interpretation, however, appeared increasingly constrained. One of the first indicators that 3I Atlas deserved exceptional scrutiny was its velocity. It was moving through the solar system faster than any previously recorded interstellar object, significantly exceeding the speeds of both Oumuamua and 2I Borisov. Velocity matters because it amplifies everything else. Thermal stress, mechanical strain, and interaction with solar radiation all scale with speed. Objects composed of loosely bound material are not expected to remain stable under such conditions for long. Yet 3I Atlas did not exhibit the kind of rapid degradation that might be anticipated. Its coma remained coherent, its jets persisted. Structurally, it behaved less like a fragile aggregate and more like a body with internal resilience. That resilience raised immediate physical questions. Traditional comet models describe nuclei as porous, low-density mixtures of ice and dust with minimal internal cohesion. These bodies survive because they move slowly and spend most of their existence in cold, distant regions. An object traveling at extreme interstellar velocity should, under those assumptions, be prone to fragmentation, especially as it approaches perihelion. But no such breakdown was observed. Instead, the object maintained consistent activity over time, suggesting either an unusually compact structure or physical processes not fully captured by standard cometary frameworks. Observation strategy became a point of quiet concern. Early high-resolution imagery from the Hubble Space Telescope confirmed the presence of a coma and directional features, but systematic monitoring did not immediately follow. The absence of continuous early observation was notable precisely because early data is often the most revealing. Before intense solar heating reshapes an object's surface, initial behavior can offer clues about composition and structure. That opportunity was only partially utilized. When routine imaging resumed later, it did so at a much higher cadence, raising questions about why such frequency was not applied from the beginning. The geometry of 3I Atlas's activities soon became one of the most revealing aspects of its behavior. In comet science, the shape and orientation of jets and tails are not cosmetic details, they are diagnostic tools. These structures are governed by a combination of solar radiation pressure, interaction with the solar wind, the distribution of volatile material on the nucleus, and the object's rotation. Because these forces are directional, cometary features are highly sensitive to changes in viewing angle. As Earth, the comet, and the Sun move relative to one another, the appearance of jets and tails typically shifts in predictable ways. Astronomers rely on these shifts to infer everything from rotation periods to surface activity patterns. Opposition events are especially valuable in this context. When Earth lies nearly directly between the Sun and the object, the geometry simplifies dramatically. From this vantage point, the observer is looking almost straight down the Sun-object line, minimizing projection effects. Any jet driven primarily by solar heating should lose its parent directionality, collapsing into a more symmetric glow around the nucleus. In other words, opposition acts as a natural filter, stripping away perspective illusions and revealing whether a feature is truly sun-driven. For most comets, this geometry resolves lingering ambiguities. That is precisely why the behavior of 3I Atlas during its near-perfect opposition drew so much attention, because instead of simplifying, its structure refused to conform. In January 2026, 3I Atlas entered one of the most precise oppositional alignments ever recorded for an interstellar object. The deviation from perfect alignment was only about 0.69 degrees, a geometry so rare that, according to Avi Loeb, only one comparable case exists in historical comet observations. This alignment should have acted as a diagnostic test. If the dominant jet was driven by solar heating, its appearance should have changed dramatically. It did not. Processed Hubble images taken before, during, and after the alignment showed that the jet remained offset, maintaining a consistent orientation regardless of geometry. This persistence strongly undermines the interpretation of the feature as a sunward-facing jet. Instead, it points toward an alternative explanation, an anti-velocity tail, composed of material trailing behind the object along its path of motion. While such tails are not unheard of, they're typically secondary, faint, and short-lived. In 3I Atlas, the feature was neither subtle nor transient. The implications of this are significant. An anti-velocity tail implies that the dominant forces shaping the ejected material are not purely solar. Instead, they may be tied to the object's motion, rotation, or internal processes. This brings rotation back into focus. Early estimates placed the rotation period at around 16 hours, but later analyses suggested a much faster period, closer to 7 hours. Fast rotation would help explain the stability and directionality of the observed jet, but it also demands a mechanically robust nucleus. Loose aggregates do not tolerate high rotational speeds well. They tend to shed material or disintegrate. At this point, conventional explanations begin to strain. Jets, in many astrophysical contexts, are associated with magnetized, rotating bodies interacting with surrounding plasma. From protostars to compact objects, the combination of rotation and magnetic fields produces structured outflows. While it would be inappropriate to draw direct analogies across such vastly different scales, the underlying physics does not vanish simply because an object is small. If 3I Atlas possesses conductive material or remnant magnetization, electromagnetic forces could influence how material is expelled and organized. This is where broader modeling assumptions come into question. Much of small-body astronomy still treats space as a domain dominated by neutral gas and dust, with gravity as the primary organizing force. In reality, space is overwhelmingly plasma, and electromagnetic forces often dominate interactions at small scales. Plasma effects are well recognized in solar physics and space weather, yet they're frequently sidelined in discussions of cometary behavior. If 3I Atlas is interacting with its environment through plasma processes, then existing models may be missing critical variables. The material released by 3I Atlas adds another layer of complexity. As it passed through perihelion, the object shed dust and gas along its trajectory, forming an extended plume that now stretches through space. Orbital projections indicate that Earth may encounter portions of this remnant material months later. While such encounters are typically benign, producing meteor showers or subtle atmospheric effects, the interstellar origin of the material introduces unknowns. The lack of public emphasis on this aspect is notable, particularly given the object's unusual behavior elsewhere. Data accessibility itself has never been the central issue surrounding 3I Atlas. Observations from the Hubble Space Telescope are released publicly as a matter of policy, and in principle, anyone with sufficient technical skill can retrieve, process, and analyze them. In practice, this means that the raw information needed to evaluate the object's behavior has been available all along. What has been revealing is how that data has been interpreted, emphasized, or quietly deprioritized once it entered the public domain. Some of the most detailed visualizations of 3-eye atlas, highlighting the persistence and orientation of its jets across changing geometries, have come not from institutional press releases, but from independent researchers applying standard calibration, stacking, and filtering techniques to publicly available datasets. This contrast has drawn attention to a subtler dynamic. The issue is not secrecy in the conventional sense, but selectivity. Certain interpretations, particularly those that align comfortably with established cometary models, are repeated and reinforced, while alternative explanations that raise deeper physical questions receive little acknowledgement. The same images can support multiple lines of inquiry, yet only a narrow range tends to appear in official summaries. As a result, the public-facing narrative conveys a sense of closure that the data itself does not fully justify. This gap between observation and interpretation creates an impression not of hidden evidence, but of uncertainty being carefully managed. Managed uncertainty is not inherently deceptive, nor is it unusual within large scientific institutions. Organizations like NASA operate under significant constraints, maintaining credibility, justifying public funding, and communicating complex science without undermining confidence in established knowledge. Openly emphasizing anomalies can invite misinterpretation, sensationalism, or premature conclusions. It can also force uncomfortable acknowledgments about the limits of current models. Classification systems exist precisely to provide order and predictability, allowing scientists to communicate efficiently and build upon prior work. When an object resists those classifications, the institutional instinct is often to emphasize what appears familiar rather than what remains unresolved. Interstellar objects complicate this instinct in fundamental ways. They originate in environments we cannot observe directly, and may have been shaped by processes that do not operate, or no longer operate, within our own solar system. Their physical histories are not constrained by the same evolutionary pathways that govern comets and asteroids formed around the Sun. As a result, applying familiar labels can obscure as much as it clarifies. In the case of 3-eye atlas, the tension between the data and its presentation highlights a broader challenge: how to communicate genuine scientific uncertainty without destabilizing the frameworks that make large-scale research possible in the first place. None of this requires extraordinary conclusions. There is no evidence that 3-eye atlas is artificial, technological, or deliberately controlled. But the absence of evidence for such ideas does not negate the presence of unresolved anomalies. Science advances by confronting those anomalies, not by minimizing them. When unexpected behavior is consistently reframed as expected, opportunities for genuine understanding are lost. As 3-eye atlas continues its journey out of the solar system, many of its mysteries will remain unresolved. The object will fade from view, leaving behind data, interpretations, and unanswered questions. But its legacy may prove more important than its physical nature. It has exposed the limitations of existing models, highlighted the importance of early and sustained observation, and revealed how institutional narratives can lag behind observational reality. The most consequential question raised by 3-eye atlas is not what it ultimately turns out to be, but how its anomalies were handled. Interstellar objects will visit the solar system again. When they do, the response to 3-eye atlas will serve as a precedent. Will future anomalies be explored openly and aggressively, or quietly absorbed into familiar categories? If something is being obscured here, it may not be evidence itself, but the discomfort of admitting how much remains unknown.